Good afternoon, everybody. Zishan said I'm Ron, and I work on types. So I'll tell you a little bit more about myself in a bit, but I just wanted to kind of set up the stage, which is that a lot of programmers here. I write lots of code, like 10 lines a year or so now. So I have lots of insights into how this works. But back in my older days, when I was actually writing more code, I came to both have a love and hate relationship with types, which is, I think, why I work on types and not types at the same time now. Call it schizophrenia. But you can look at types and typed programming languages in multiple different ways, and I just wanted to kind of highlight kind of these two kind of views of the idea of having a type discipline. And one of them is like, the discipline like strengthens your mind and helps guide you so that you can break things and like shoot people across the wall. But then on the other hand, like, you can think of a discipline as like that thing that keeps you from doing wrong and makes you sad. So, then you find yourself getting your hiney smacked in modern art. For instance, a lot of people who are really into programming and especially typed functional programming languages like this idea of saying like the types will guide your program and thinking in types will help you program well. So this is just an example of the Idris language and this idea of type-driven development. But I'd also note that the place where I really first came to appreciate type-driven development is in the Racket programming language. There's a book called How to Design Programs, which is basically how to program with types without a type checker. So it's like high wire walking for like people who don't feel like using training wheels. So on the other side, you have this idea of type discipline and how type checkers that you work with kind of, sometimes they drive you crazy, sometimes they help you out a lot. And one case here is just like, yeah, your type checker tells you that you gave it something that has type string and it wants type string, list. And you're like, oh, I know how to fix this. Let me just put brackets around it twice and then then carry on. You're like, it like reminds me of my old C programming days where they had this idea of what was called a 3-star programmer, where you're like, oh, just add more stars and then like hit compile. So you can do the same thing in a functional language. In this case, the real answer is you swapped your arguments. Maybe you want to switch them the other way. So that's kind of the life of a person programming with types. And as a researcher, I spend a lot of time kind of thinking more in the abstract about them. So this talk is to try and give you kind of a flavor of a theoretician's point of view on how types work and how that kind of style of thinking can help you think about even types in programming and give you some insight into what kind of type systems researchers do. So as Zishan said, I'm a professor at University of British Columbia, and I've spent a lot of time working on mixing, static, and dynamic typing. And in order to do that, I've spent a lot of time trying to think about what is going on with types. There's so many different views, and as a theoretician, you want some grounding, so you end up spending a lot of time reading lots of papers. Not necessarily visiting the town of reading, but whatever. So I put together this list of papers that I think have definitely influenced me in my reading about types. And I should note that this is not the definitive list of papers on types. There are papers from earlier. There are definitely papers that have been written within the last 13 years that are really significant. But this was just a really interesting window into types. So having spent a lot of time kind of digesting these papers and reading them, I guess I am that kind of person who sits around with a beer and a paper and is like, yeah, like papers. And you're like, it's the weekend. What am I going to do? Read another paper. Like, yeah. So it's kind of addictive. But today I'm going to kind of talk about mostly I'm going to focus on what I think is kind of one of the great papers on types in programming languages that just happened to come out in the 1970s. And there's a number of other papers here that I think are also really significant, but you can only cover so much in a period of time, and I decided that I'd focus on mostly one and then talk about how it relates to some of the work in the others. So throughout the talk, I kind of hope that I'll bring a few themes that arise when you're thinking about types and type systems from a theoretical point of view. And one is this idea of syntax as, we all know about syntax because we spend all our time arguing with one another about what's the right syntax for a programming language. But really here what I mean is this idea of symbols and symbol pushing, really. that basically symbol pushing is what computers are really good at to a certain extent. I mean, when McCarthy came out with Lisp, he really wanted a language for writing functions that operate on symbolic expressions. And much of what we do in computing and programming is really building symbolic representations of ideas and then computing over them. And much of what you do with type systems is that, and it really relates to how they get implemented and how you reason about them. But just because you can throw symbols up doesn't mean that you have any idea what they mean. And so at some point, you really need to talk about semantics. And semantics is just a highfalutin word for meaning, like, huh? So I'll spend some time talking about what's the relationship between syntax and semantics. And this is a really big deal in basically any kind of programming. I mean, programming languages just happens to be writing programs where your data is programs, which is kind of cool if you like eating your own dog food. But any program you write is going to have some sort of notation and some sort of interpretation. And then the last is pragmatics. So in the world of linguistics, they often talk about these three things. And really what I mean here is that at the end of the day, you have some goal that you want to achieve, and you will do what you need to kind of bridge that last gap to getting your job done and focus on that a bit. So some notions of what are some of the pragmatics from a theoretician's point of view, which may not be the same as from a practitioner's point of view, come up. So onto the meat of the talk. So this paper by HindleyMilner it's a great, and as you can see, it's from the 70s. I was actually alive when this paper was written. That didn't help me understand it. But HindleyMilner, just like a quick side note on him, he's a really brilliant British computer scientist. He's no longer with us, unfortunately. But he did a lot of work on theorem proving, and he wrote this LCF theorem prover. And the ML programming language came out of trying to solve the problem of how do I write a theorem prover and how do I write techniques for writing theorem proving. So it's like you do one amazing thing, and then you do another amazing thing so you can get the first amazing thing done. And then he went on to work on concurrency and came up with these couple of systems, especially the pi calculus. And for his body of work, he was awarded the Turing Award in 1991. And I always thought it was really cool that this dude who blows your socks off, he didn't have a PhD, but he was just really passionate about his work, and he learned what he needed to do and thought really hard and tried to. You read his papers and you get this sense of intellect, of really kind of trying to think hard about problems and conceptualize them. So I really enjoy reading his papers and seeing how he thinks about things. Better with a beer. Not too many, or you won't understand. So the paper, in the community on types, this is kind of like, oh, this is the HindleyMilner type inference paper. Now, just out of curiosity, how many of you have programmed in ML or Haskell or standard ML before? Okay, so there's quite a few of you, and you've enjoyed the experience of not having to spend all of your time writing down type annotations, and somehow the type checker does things. And this paper kind of codified a lot of those ideas, and it's been viewed that way. But I mostly want to talk about it from a different point of view, its place in the world of type systems, which is that in many ways, this paper really brought together what I'd call a conceptual blueprint for analyzing types and type systems, for how theorists think about types. And I'm hoping that I can kind of convey some of those ideas through a walk through some of the details of this paper. So let's just dive in. Now, so unlike the last talk, there's probably going to be a lot more math than code in this one. There's a lot of symbols, but bear with me. We'll kind of walk through it, and you'll see that your intuitions as a programmer really help you understand a lot of this stuff, and the math starts to get you at the corners. So as long as you don't need to prove any theorems, you can be like, yeah, I can kind of get what's going on if I put my programmer hat on. Yeah, it's just Haskell code. It just happens to be undecidable, whatever. So as I'd alluded to, we start with the syntax, which is in the top box. And really, it's just a data type. It's just data. You have trees. Programming language theorists don't worry about parsing. We're not how many spaces or what should your pretty printing be like. We just skip the whole pretty printing part. Let somebody else do it like the previous speaker, and then just give me an abstract syntax tree, and then I will operate on that. So this is just a data representation in Racket of that symbology up there. And as you can see, that one's a lot smaller than that one, which is, I think, why PL people really like to write that way. Because like, you could basically like, translate that into Haskell, translate it into OCaml, write a class hierarchy in Java, and that's your syntax. And it's meaningless just as syntax. So this concludes the coding part of the talk. Okay. I figured I should have some code in there. So going back, down below we have this, this is the semantics. So this is really the definition of what these programs that you can write in that language up above mean. Like, if you give me one of these abstract data types, what can I do with it? What's the result that this program's going to produce? And it's basically an interpreter. Like, you could almost take this notation and say, yeah, it looks a lot like the Haskell programming language, and if you look in the bottom left corner, the cursive E is just like, yeah, that's the name of my eval function, and I just happen to have Unicode, so I'm not going to bother writing eval. So it's like mathcal E. And then the fancy brackets, which are called Scott brackets after Turing Award winner Dana Scott, it's basically just notation for here's how we do pattern matching on our data structures. And so each of the equations up there is like pattern matching your data structure apart into all the pieces that make up your data. And then the last thing is called an environment, and that's essentially just a lookup table, and it's a mapping from variables to values. So the idea is that you have a type signature at the bottom, but it's like a math type signature, and it says that if you give me an expression in my language, what I will do is return you a function. And what the function says is, tell me what environment I am in. Like, what's the world around me like? What's the value of x? What's the value of y? And then I will give you an answer. And the answer happens to be like some stuff in math world. So you can think about this as basically an interpreter from this EXP language to math. And this ends up being kind of a theme throughout. And it is kind of interesting that given any arbitrary piece of code, you get back like a meaning, and the meaning is like, tell me what the world is like, and I'll tell you an answer. And this theme will arise again later. So interestingly enough, at the core of this ML language is it's a dynamic language. It has all of these checks in its definition. And if you look at the second line, what it's basically saying, the first thing it says is, well, V1 is basically what happens when I evaluate the argument position of a function application. That's a function application. And then if it's a function, then keep going. If not, then go down to the next line. Wrong, like you have a type error, like a Python-style error. But if it's OK, then double check running the second thing. And if that like threw a type exception, then throw a type exception. Otherwise, take the first argument, and it's a function, and then pass it the result of the second argument. So if you've ever written an interpreter by chance, actually, I'm curious. Could you raise your hand if you've written an interpreter before? OK, so there's a few of you have. The rest of you probably actually have but don't know it. Most programs are really interpreters. But the basic idea here is just like walk the tree and then interpret. And we happen to implement EXP functions using math functions here. And if you were to ever implement an interpreter, you'll find that that's a really cool trick that you can do too. Like, oh, I'm going to implement my Python functions using Haskell functions, or vice versa if you're sick. Just kidding. You can perfectly well do that. And especially, like, interestingly enough, there's an interesting implementation of JIT compilers using Python called PyPy. So you can implement lots of languages in Python. Anywho, another thing I'll note is that basically, every program runs. Like, as long as you don't have free variables floating around, like, you better have some meaning for your variables, and that's what the environment is for here. So it's basically all closed programs run, and you don't get wrong if you try to look up a variable. Like, you always have some meaning for it. So that's kind of the kind of core of this dynamic language. And now, kind of the goal is, how do we make those red circles go away? In Milner's paper, he talks about like, yeah, you run into these silly problems where you decide to call try and apply a number as if it was a function and give it an argument, and bad things happen. And wouldn't it be nice if that kind of error just went away? Yeah, that's what type systems are for. So people had been doing this for long before this paper came along, but he said, how do we try and take an analytic approach to thinking about and proving once and for all that, like, our type checker does good things and keeps us from having certain kinds of errors happen, specifically the ones that are listed as wrong here. There's nothing on this slide that says divide by 0 produces wrong. You just say, like, it produces divide by 0, and that's just not wrong. So when I say that well-typed programs don't go wrong, you're like, yeah, but they divide by 0. You know, like, you know, don't worry about that. So let me start talking about types. Now, I've got this language, and interestingly enough, there's like a bunch of prose up here, and he's like, oh, the syntax of type is as follows. And it's basically just another definition of a syntax for types. And I listed as 2 things here, and it really is, again, a data type. But he separates his world of types into 2 different kinds of types. And this is really for reasons of the kind of language that he's trying to define here, the way that ML's type system works. So he has monotypes, which are basically, you know, types that you'd see in most any language. You've got integers, you've got functions from integers to booleans, functions from integers to integers to integers to integers, etc. And then he also adds this idea of polytypes. He adds type variables. You're like, oh, okay, so just stir in some type variables and then keep like adding arrows, and now I've got these new things, and I give them a name called polytypes. You're like, okay, and those are the types. And so in this case, he uses Greek letters, because PL people can't help but use Greek letters. As a result of studying too much type theory, we know them all. We know the difference between kasai and kai. It's kind of disturbing, but it comes up. So now you have types like alpha to alpha and alpha to beta to alpha, which is not the same thing as int to int. And then you have alpha to int to alpha. It's like, okay, we're done, we can go home. No, we can't, because all I've done is written down more syntax, right? This is just a data type. So what do these things mean to us? You know, like if somebody came from Mars and said, like, what is this alpha, arrow, beta, or alpha? Well, if somebody came from Mars, they have other things other than interpreting types. But assuming that they were into programming, you know, you're wondering, like, what do these things mean? Like, what does int mean? What do these types tell us? So we have to give or what Milner does is he gives semantics to his types. He says they're meaningful things in the world, and it's up to us to decide what they mean and then be able to say something about that meaning. So he starts by, in a place that to me seemed weird, is like, okay, so our programming language, you know, you throw in expressions and values pop out. And let's give meaning to the values that pop out of running your program. And it's sort of like, yeah, but you know, when I grew up, I always typed my programs, not the results of them, so what's that about? And it's like, well, this is a starting point, because if you think about it, the values that come out of your program are in a certain sense the meaning of the programs. So you want to kind of understand what the types have to do with the meaning of your programs, and then worry about the syntax of your programs later, and we'll get there. So he starts by giving this definition of the semantics of his monotypes, the ints and the int, arrow, int. And once you start looking at it, you're like, yeah, a lot of this is sort of intuitive, but then there's like, oh, some stuff that's a little weird. So one thing that happens is I had mentioned that math works a little funny, and there's a value in your language which is basically infinite computation. It's like, yeah, you can just like have infinite computation in your hand, pass it to your friends, like, you know, share it, and you're like, okay, that's a little funny, but you know, this is math. Math doesn't care about non-decidability. So any non-terminating computation has basically every type. So like, yeah, if I have a value and it's non-terminating, then I can say it's an integer, I can say it has type bool. And you're like, well, why is that okay? So in a certain sense, it's okay because, you know, that ship has sailed. It's not coming back, right? So you're like, yeah, you know, you can give me my infinite computation and then add 5 to it, and I'm like, it's not going to go wrong. It's just going to go. So that's kind of, essentially a design decision, and like I've decided that the meaning of my types is that, yeah, maybe some programs don't terminate, but I'm going to be okay with that. And I'm going to say it's okay to say that something that doesn't terminate has type int. Same with functions. Now your basic constants in your language, he uses this symbol bi, and he's really referring to things like 42 or false. And he's saying like, yeah, so a value has type int if it's an integer. And a value has type bool if it's either true or false. So this is kind of mathematizing things that feel pretty obvious. Now, when he gets to functions, I think it's really interesting because aside from the non-terminating functions, he says something like basically, a value is a function if it's a mathematical function. That's what the VEF thing is like. Yeah, make sure it's a function. If it's not, then it definitely doesn't have a function type. And if it's a function, then make sure that if you give me any value that has like the domain type, where the domain is like, if it's int, then it's a number. If it's bool, it's a Boolean. But it might also be a function type, right? It could be like a function from int to int, which is also defined in this definition. It's all like this like recursive, never-ending weave, except it ends because types shrink. And the definition, the type on the left in this definition is bigger than the types on the right, so you work your way down. So it's basically saying, as long as this function takes something and then produces a value, if it produces a value, then that value behaves like the second thing, this eta, then the function has that type. So this is kind of mathematizing a like behavioral property of a program. So like to me, this is very much like what people call duck typing. You're like, yeah, if it walks like an int arrow int and it talks like an int arrow int, then it has type int arrow int. So that's kind of, now I've given meaning to what it means in my language in terms of the semantics of values, what it means to have a type. And then, yeah, every non-terminating computation has every type. Interestingly enough, wrong does not have a type, and that ends up being important. Wrong is a value in the language. So then, all that was talking about was the monotypes, right? You're like, oh, okay, int arrow int, we're cool. Int, we're good. But what about this like alpha arrow alpha or alpha arrow beta arrow alpha? No problem. Okay, what's going on here? This is like a bunch of notation. So in English, what this is basically saying is, so sigma is one of these polytypes. And it could be like all monotypes are also polytypes, but it might have variables in it. And then this sort of less than symbol is saying like, is mu, which is like a monotype, is like an instance of sigma. And so it's basically saying V has this like polytype if every concrete type that looks like this type with type variables in it is also a type of V. So to give you like a concrete example that might make it easier, which helps with me, you could say like, let's say, what does it mean for V to have type alpha arrow alpha? Well, you're like, if I have a value, it has type alpha arrow alpha only if it has type int arrow int and bool arrow bool and int arrow int arrow int arrow int, etc. Right? So give me any type, and as long as this thing can behave according to this behavioral specification of blah arrow blah, then V has that type. But it has to satisfy all of them. Make sense? So this is basically going to be a function that takes something and returns the same kind of thing, something that behaves like it, as far as we know. So in a sense, what we've done is we've built up this tower of meaning for our types. And this is part of why this monotypes, polytypes was separated. The monotypes, you're just like, yeah, I know what int is, I know what int arrow int is. And then the polytypes are, now that I know what monotypes mean, this allows me to talk about lots of types at the same time and say this one thing has lots of types. And in fact, there's an infinite number of them. Okay, so all this time I've been talking about how do we type values, these things that pop out of our program. So it's like, yes, my values from running a program are meaningful, and I can describe their behavior, how they can be operated on, both in terms of monotypes and polytypes. So now it's like, well, yeah, but I want to talk about my programs. I don't necessarily, by the time I get my value, the ship has sailed. Like, please tell me about my programs before I even run them and get values. So, how do we give types to expressions? Well, yeah, Milner does this. But in a sense, his main goal in his paper is to try and focus on his main theorem, which is that like, whenever my type checker says it's typed, then things don't go wrong. And he sort of glosses over this point that like, yeah, expressions have types. We can kind of give types to expressions. So So in this talk, I'm forced to do a little bit of violence to his paper and kind of butcher it and then put back together this sort of hidden story of what the types of expressions are. It's there, but he didn't tell the story that way. And it's quite reasonable because really this was the first paper, at least as far as I know, that does anything close to this, that really does this tight connection between programs, gives meaning to types in terms of how programs behave, and then talks about what your type checker has to do with any of that. We haven't even talked about type checking yet, right? Hey, we haven't even talked about how do you type an expression. So here I start stealing bits of Milner's paper and then kind of putting them together to describe. So he first starts with this idea of like, we need to be able to, we want to be able to talk about what the type of an expression is, not necessarily an entire program, but like a piece of code, a chunk of code. And that chunk of code may have variables in it that aren't bound. They're like free variables. So you need to kind of account for that. Like, how do I even talk about a piece of code that has free variables in it? So we start by saying, well, we can build a list of what variables show up in that piece of code. And he just calls this a prefix. So then what he does is he says, if I have a piece of code and it has free variables in it, then I probably want to say something about what do I know about my piece of code, assuming some things about what those variables are going to be bound to. And so all you do is you say, well, I'll just assign a specification to each of those variables. I'll give it a type, which is this kind of language for talking about behavior. So he creates these things called type environments. Now, as a side note, I'll note that if you look in kind of modern papers or books like Benjamin Pierce's Types in Programming Languages, they don't use this P over bar. I mean, Milner was treading somewhat new ground, but he also hadn't interacted as much with logicians yet. He found logician religion later. But in most modern notation, they'll use this capital gamma for this thing that instead of mapping variables to values, it maps variables to types. So descriptions of behavior of values. So then he describes this idea that you can say, what does it mean for a value environment? Remember that our semantics for our language has these environments, these ADAs. And what does it mean for one of these ADAs, a value environment, to satisfy or respect a type environment? And so a type environment says like a variable has a type. A value environment says that a variable maps to a value. And all you want to do is make sure that the two mesh together, that whenever all the variables over here say that they have these types, that the values that the environment points to have values that satisfy those specifications. So from those pieces, this idea that I can say that a value environment satisfies a type environment, and I can already talk about the idea that a value satisfies a type, then I can now say, what does it mean for an expression? And so I put a D here. D is the same thing as E, but Milner just happened to say, yeah, we use D and E interchangeably, and when I cut and paste out of his paper, there was a D there, and I was like, why is there a D there? Why isn't it an E? And you dig backwards, and you're like, oh, because D's are E's, and he's making me sad in the future. So I get to pass on the sadness, and so but note that D's are E's. So he's basically saying that given a type environment, kind of a specification for variables, an expression D, so code, a piece of possibly open code, has a type if and only if for every possible value environment that maps variables to values that satisfy the types that P bar says, then if I evaluate, that's the E, that expression using such an environment, I better get back a value that satisfies the tau. So that's the semantics of expressions, and I'll kind of wax poetic about that again, because this is really the heart of his semantics of types for expressions. And this is really, what does it mean for an expression to have a type? And it's basically, if every possible value environment that meets the input spec P bar yields an output value V that meets the output spec tau, then you can say, only then can you say that P, the type environment P, under the type environment P, the expression D satisfies the type tau. It's like, this input specification says that this expression has an output specification. So it's all written in terms of the meaning of your programs, like using this E thing. Make sense? So this is kind of a sort of semantic model of your types. You're talking about types as meaning behavior, not like, my type checker gave me an error about string list, and it's more like, these are behaviors. So, okay, great. Now we have a definition of what it means to be well-typed. So all I have to do is if you give me an expression and you give me a type environment, I just have to look up all infinite value environments, like find how many of them satisfy my type environment, and then like run my program, and then see if the value that pops out satisfies an infinite number of behaviors that matches my spec. Piece of cake. I should note that this is in a sense like it's really a static analog to this idea of running your program. That usually you take one environment, you run your program, you get a value, but now what we're saying is like for a class of environments that all satisfy a particular spec, running my program produces a set of values that satisfy this spec. So it's kind of a global statement about lots of inputs and outputs. And it's so undecidable. Like, no. You can't just like grab all environments and check in the general case. So it's like, well, okay, so what do we do? Like, I've got this great definition of what it means for something to have a type, but I want to actually do some type checking, or like I want to be able to somehow say that things are okay. So that's where we're going now, but it's going to be in a couple of steps. So just to recap, what we've done so far is we gave a syntax and semantics of a language, and then we gave a syntax and semantics of types, first on values and then on the code that you write, the resulting values, and then now we have types for code. And so the question is, how do I even check that a program has types? And of course, I can't do it in general. I need to approximate somehow. So we go to this thing that's called a syntactic type system. And now, when we talk about type systems, you're often like, the type system is the thing that my type checker doesn't complain about whenever I give it a program. That's kind of like a loose thing. But we can be a bit more rigorous about what's called a syntactic type system. And I'm emphasizing this idea of syntactic because we are now going to engage in symbol pushing, that thing that computers are really good at. So on the left is kind of Milner's definition of this idea. What does it mean for a p-bar to syntactically, type environment p-bar to syntactically say that an expression E has a type sigma? And it's like mumble, 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 mumble. That's why it's small. So that was an early definition of it, but later on, as Milner found out more about how logicians think about proofs and building proof systems, he adopted that notation, and others had as well. And so this is still kind of small, but it's a bit more structured. There's like a bunch of things with horizontal bars and names to the left of them, stuff on top and stuff on the bottom. So I'll note right now that basically, for all practical purposes, the thing that you're looking at on the right is a description of a data type. It's like a recursive abstract syntax tree kind of thing. But it happens to be somewhat context sensitive. So you can't just hook any two things together with premises. There's going to be some conditions. And so typically, like if I implement this in Racket, I need to add a bunch of like contracts so that every time I try and add something together, then I do a runtime check or die and don't build the tree because then the tree would be bad. If you happen to have a language with a really sophisticated type system like Idris or Coq, then you can actually encode in the type checker those rules so that you can basically build proofs as objects, these context-sensitive things. And this is sort of the secret sauce behind Curry-Howard-based theorem provers. So let me just give you kind of a brief comparison between these two type systems, the semantic type system and the syntactic one. And right now I'm just going to kind of focus on functions. So the two rules at the bottom are describing kind of how the syntactic type system interacts with functions, whereas this one statement at the top kind of talks about the behavior of functions in terms of running programs and observing behavior. So the one on the bottom, basically what it says, and it's a little small, but it basically says, if I had a piece of code and I was assuming an environment where some particular variable had a type, and then that meant that the body, this piece of code, produced this output behavior, then I could just wrap a lambda around it, and that function would have that function type. Now, I'm speaking intuitively in terms of how we think about typing. And if you thought about it, you'd say like, yeah, of course, if the body of the body of my function, given this particular type for a variable, was going to behave a certain way, then putting a lambda x says that like it should have that behavior of the function. Now, this is like our intuition about a step of reasoning, and we've encoded it in a bunch of syntax. So that's like a syntactic proof. And while I sure hope I'm right, like I really hope my language is sane and acts this way, I'm on the hook to prove that that's true. Similarly, on the other side, what it basically says is if I have a function of type like tau prime arrow tau, and then I have like, an expression whose type is tau prime arrow tau, so it should intuitively produce a function, and another expression of type tau prime, then if I apply the first one to the second one, I should get the output result. So you're like, yeah, intuitively that should be true. So again, I'm on the hook to prove that. Now, interestingly, in both cases, you can think about these rules with respect to the syntax of your code. Like, the things on the top are smaller code than the things on the bottom, right? On the left, you have some expression. On the bottom, you have a function with that as the body. On the right, you have two expressions. And on the bottom, you have a function application of the two hooked together. So what this is describing is a way to reason about the behavior of my code by thinking about the behavior of small pieces and what happens when I hook them together. So I can think about how my code behaves syntactically and in pieces. And so modularly, one piece at a time, and then compositionally by hooking them together. And that's really one of the secret sauces of type systems in general, is this syntactic idea of reasoning about how my program runs by thinking abstractly about the behavior of each piece. This is kind of the heart of type-driven development. And it ends up being attached to the meaning in terms of behavior. So now we have some due diligence to fill out, which is how do we relate this thing down here, description for building these proof trees, kind of like in geometry where you have like lists of proof steps, and then you say by whatever rule, and we have to relate that to the semantics. So we do that with a proof that's called semantic soundness. And basically, here is Milner's proof of this semantic soundness that connects type assignments, our trees of proof rules, to actual behavior. And I'm rewriting it in slightly, almost more modern notation. And it's basically saying, if I have a data structure who's like, that is a proof of blah, 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 that's what the thing with the single turnstile after the P on the left is, then something meaningful is true in the world. And you can see that both of these look exactly the same. I defined the one on the left because Milner didn't bother doing it, but this is essentially what that theorem is saying, just slightly factored differently, which is if I write down a proof, it's actually true about the behavior of my code. And it really does say, like, every proof of type assignment says something meaningful about my code. And this relates syntax to semantics. Now, conveniently as a corollary, we achieve like Milner's big goal, which is like, by the way, wrong has no type, so every well-typed program doesn't go wrong. This was his goal, is like well-typed programs don't go wrong, and he could prove that by having come up with this behavioral specification. Now, it's useful to note that this was already true about the semantic system. It's just that he didn't bother like bringing it out until he already connected the syntax to the semantics. And he's like, now I know that if I can build one of these proofs, then I know that my code won't go wrong. So all I've done is describe this sort of data structure, right? It's like, oh, I've described a data structure, and I said, if you build me a data structure that when I look at it, it says something about my code, then something's true about my code. And the question is, how do I build a data structure that says something about my code? That's what type checking is. So Milner's language has this type inference thing, which really every language has to some extent. You have a program. I didn't give you, like when I program, I don't program by writing proofs of typing trees. What I do is I give you a bit of code, and then what your type checker does is try and find a tree that corresponds to your code. And it just happens to be particularly sophisticated in Milner's case. So he develops this algorithm called algorithm W, and there's algorithm W. You can see about as much detail as you need, which is it takes a bunch of lines, it's describing a bunch of computational steps, and what you need to know is, like, is it any good? Okay, you gave me an algorithm, it takes a program, and then it makes a claim. It says, like, yeah, this program has a type, here's a type. Or no, there's an error, I can't type it. So this is where another proof comes into play, and this is what he calls syntactic soundness. And what this does is it connects the result of type checking to this definition of type assignment, these trees. Now, in turn, type assignment is connected to through semantic type soundness to behavior. So it's this two-step thing. I have a program whose job is to take programs, generate typing trees, and then I have a theorem that says that they mean something. So what this basically says is that if algorithm W returns a type assignment, says this program has a type, then I, the person who writes the theorem, could build a corresponding proof in this case. And what you do is you basically discover that, yeah, what the algorithm's doing is its stack trace is building the tree, and then it's throwing it away because you don't actually care about the tree, you just care that your program has the type. You care that it has a type, which then means it doesn't go wrong. So let me kind of bring everything together about what's kind of going on in this mathematical model. We, at the top level as a programmer, you're thinking about, I have a type checker for my language, and it performs computation. I give it a program, and it gives me like a thumbs up or thumbs down. Well, thumbs up with a type or thumbs down, like you need to add more list brackets around your S. That, in turn, is connected to this idea of what is a syntactic proof of types assignment. And it's really like a proof that a program has a type following the syntax of your program. And the nice thing about that is it really allows you to think locally about the behavior of your program. You don't have to take the whole program and say, given a whole program, what can I find out about it? It's more like, by looking at pieces, modules, libraries, and then hooking them together, I can understand something about the whole program, and I can split it up across an organization and provide interfaces. And then the last bit is that Milner came up with a meaning for his types. What does it mean for an expression to have a type? Like, yeah, if it has type int, it better diverge or produce a number, or throw an exception, or leak my passwords, or given any programming language, it's up to you to decide what the guarantees are that your types give you. To some extent, they seem to pop up very similarly again and again, but at the end of the day, you ultimately have to decide what the definition is and whether or not you can build a full thing that can stand on top of that definition. So in many pieces of work on type systems, the part at the top where you have this type checker and this type assignment is viewed as kind of obvious. It's like, if you're not doing crazy type inference, then you look at your proof rules and you say, do recursion the other way. Like, I can see what my program looks like. I know which rule I'm going to use. I need to search for something that's smaller for the other pieces. Milner's is more complicated because you didn't tell him what the types were. So he has to do something much more sophisticated, which is why he needs to talk about the algorithm and talk about the proof. In many cases, you're like, turn your head upside down, type checker. The other thing is that, as I'd mentioned, at the end of the day, what Milner really wanted was he wasn't trying to give a semantics of types. That wasn't the main goal of the paper, and it's not really what he talks about in the abstract of the paper. What he talks about is, I prove a theorem that says that well-typed programs don't go wrong. He doesn't say that I prove a theorem that says that well-typed programs behave according to what my types say, because that really wasn't his main focus. But it's a useful thing to know and to think about, and it just happens to not be what he was doing. And much work on type systems really doesn't worry about the semantics of types. It just really worries about, I need some way of proving that if my type checker says something, then well-typed programs won't go wrong. And so later work that I'll talk about just very briefly kind of comes up with a way of doing that, like skipping that step, like, don't bother giving meaning to your types, your informal understanding will do, and then we'll go from there. And then you can prove that your type system guarantees this sort of non-wrongness soundness thing. So yeah, this is kind of a particular mental model for thinking about types as somebody who's being very analytic and precise while analyzing the semantics of a programming language. And this is much of the work on type systems that theorists do, builds on top of this work, and as you saw, like some pieces collapse depending on the needs of the researcher. So at the end of the day, I asked, like, what are types? What are these things? Well, as I mentioned earlier, it's like, programming languages, they have these syntax, like you have to write something down. They have semantics, you give meaning to them in terms of the evaluator, and then there's some pragmatics. At the end of the day, I want to run closed programs, with maybe like library functions. Interestingly enough, types have syntax. There's these arrows, there's these things called int and bool. There's these semantics which say, what do the types have to do with the behavior of my programs? And then there's some pragmatics. It's like, it better be true that they go wrong. It better be true that, no, not that they go wrong. That's a sweet type system. It better be true that they don't go wrong. So really, a type system is a language. And in particular, it's a language specifically geared for talking about properties of programs and program fragments. So when we talk about like static checking or dynamic checking or static typing or dynamic typing, at the end of the day, we're talking about a language that is ultimately separate from the language that it's talking about. It's a different language. But the mechanisms by which we check or enforce types is what introduces sort of static checking and dynamic checking. And this is kind of the thing that it's taken me way too long to figure out. So I'm running out of time, so I wanted to just give you a brief whirlwind tour to set context for the other papers that I brought up and why I think they're important in this context. So I want to kind of focus mostly on the ones I think are the most important. The single most important next paper, in my view, came out like 20 years later almost. So things take time. And this one is called A Syntactic Approach to Type Soundness. The syntactic is really important. So Milner came up with this conceptual blueprint for analyzing types. And then people went off and started like trying to use this technique. And a few people managed to be successful. And like there were a few soundness proofs like I described, but not a lot. Then in the 90s, kabam, this paper comes along, and it really provides like a practical blueprint for analyzing types, especially with respect to proving that well-typed programs don't go wrong. As described to me by a friend of mine, Neil Krishnamurthy at Cambridge, basically, before this paper was written, like basically no one ever proved type soundness of anything. After this paper was written, it's like soundness, 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 soundness. Like a bunch of people were able to do this for various languages, low-level, C-like languages, high-level functional languages. This really came up with a nice practical technique for how to do it. And basically, everyone uses this technique. Almost everyone uses these techniques these days. If you've ever heard of progress and preservation, most of that was in this paper, and then a follow-on paper by Bob Harper from Carnegie Mellon the same year. Now, from another point of view, there's these two papers, which were about a decade apart, but are really close in flavor to one another. So the way I was describing the behavior of type, of values, you could say like, oh, like you could think of a type as being the set of values that have this particular behavior. And so Jim Morris, who wrote this one paper, he's like, no, don't do that. And like he's like very clear about it in his title. He's like, types are not sets. And what he's arguing is, and it's a beautifully written conceptual argument, is saying like, it's not that it's a matter of fact, but it's just that it's really useful to think about types as like comparing multiple programs against one another with respect to behavioral specifications. And this becomes really important when you start talking about things like abstract data types and information hiding. And the only way to prove for sure that your particular type system supports information hiding is to use this different relational description where types relate two programs to one another, not say that one program is in the type. And Reynolds came along and actually showed how to do this in math. So then the last one that I want to mention, and there's plenty more, this is actually a PhD thesis, so it's not short, but I should mention that I really like reading PhD theses because they tend to be written by someone who's just come to discover how things work, and so it's sort of close to you. Well, Amal's not, she's way smarter than me, but is able to kind of say things in a clear fashion over a lot more space with more details. And this particular thesis is really awesome, and it basically talks about, here's a practical way to do the things that John Reynolds, who's like, could do that like the rest of us couldn't, and using some techniques that are kind of very reminiscent of what Wright and Felison did, and this comes many years later. So that's the end of my talk. And I just wanted to put up basically one of the main takeaways that I wanted you to get from this talk, which is really that the way to think about types is that they're a language and their own, and that we then use that language to think about the behavior of our programs and figure out how to enforce and check them. So thanks a lot.